Welcome to the ChemDoctor, and what I want to do in this video is create a short presentation on the determination of charges on elements in ionic and molecular compounds, also known as determining oxidation numbers of elements that are within compounds. And when we're dealing with an ionic compound, usually determining the oxidation number or the charge on the various ions that are in that compound is an easier task than it is for a molecular compound, because ionic compounds, like the example I'm showing here, nickel 2 sulfide, ionic compounds contain ions, whereas if we were dealing with a compound like this, which is molecular, in that case, the elements that are in this compound are not ions, and so instead of determining charge, in this case, we're going to determine what's called an oxidation number. Now, what is an oxidation number exactly? All right, so we use the term oxidation number to basically indicate the level of electronic charge that would be associated with that element when it's in a compound bonded to another atom, because elements that are bonded to other atoms do not share electrons equally. So the electron density within a molecule is going to be distributed between elements depending on their electronegativities. In an ionic compound, it's rather straightforward, because you're dealing usually, like in this case, with a metal that is bonded to a nonmetal. All right, and usually in the case of an ionic compound, when these two elements met and underwent a chemical reaction, electrons were transferred. Usually the metals give up the electrons, and usually the nonmetals accept the electrons. So in the case of an ionic compound, it's pretty straightforward usually to determine what the charges are on the elements, because there are essentially known tricks to this. And what I mean by that is, if you look at this compound, for example, hopefully you know your elemental ions, and sulfur comes out of group 6A, for example, and in 6A the key ions there are going to be oxide and sulfide, excuse me, right? And sulfide carries a -2 charge. So when you look at this compound, determining the charge on the nickel becomes rather straightforward, because the other thing is, we understand that the sum of all the charges in this compound need to be 0. So therefore, if the charge on the S is -2, then we know that the charge on the nickel has to be +2. So we would say the oxidation state of the nickel is +2, and the oxidation state of the sulfide is -2. Now, in a molecule like CH4, we have an issue, because neither the carbon or the hydrogen are actually ionized within this compound. So how do we figure out what the theoretical charge would be on the carbon and on the hydrogen? Well, this is where the rules for determining oxidation numbers comes into play, and the student of chemistry is going to have to know those rules. All right, and so if we focus for a minute on what the rules would be for carbon and hydrogen, well, we don't know what carbon is. All right, that's our question mark. On the other hand, there is a rule for hydrogen, and it goes back to making sure that you know your elemental ions. So for elements that are in group 1A, we know that when these elements ionize, that they are going to form +1 cations. And this fact should be committed to memory. I'm just going to put 3 dots like this to indicate that this trend continues down the group. And we see that hydrogen is in group 1A, and in most cases, when we're dealing with a molecular compound, hydrogen will appear in that compound as +1. So we can set up a simple equation to figure out what the carbon is going to be, because we acknowledge the fact that whatever the oxidation state or the charges on the various elements within a neutral compound, the sum total of all those charges needs to be 0. All right, so we're going to set up a simple equation. We're going to say that whatever we have on the left side here will have to sum together to be 0. And then I'm going to let carbon be the unknown, so I'll just use its atomic symbol. And then we're going to be adding whatever the charge is, and I'm using the word charge liberally because I think one of the issues with this and learning this material for students is really wrapping their mind around this term oxidation state. So it's legitimate to consider oxidation state as being a theoretical charge. So basically what we want to know here is that when we sum whatever the charge is on the carbon to the hydrogens, of which there are 4 of them, and each one is worth +1, that the sum total of these two things always has to be 0 for this compound. So now we can go ahead and solve the equation. It's going to be carbon plus 4 is equal to 0. Therefore, the oxidation number or the theoretical charge on the carbon needs to be -4. So carbon in this compound is going to be -4. When you think about this, it makes perfect sense. Since the hydrogens are +1 and there's 4 of them, that's +4. Total net charge, then the sum of these two things is 0. Alright, now let's look at some other compounds. Alright, let's turn to another ionic compound, magnesium chromate, which is going to have this formula. And we ask the question, how do we find the oxidation number of each of the elements that are in here, which translates into how do we get the charge on each of the elements that are in here? And you see that there are 3 elements. And at this point, you freak out and run out of the room. How do we deal with this? All right, well, you need to break it down. So number 1, look at your magnesium. All right, it's out of group 2A. And again, you're going to need to know the rules for assigning oxidation numbers to elements. And the first rule is that you must have your the elemental ions must be memorized. And so magnesium is in group 2A. And you need to remember, okay, group 2A elements, when they ionize, form the +2 cations. The group 1A and the group 2A cations always ionize to equal the number of their group. All right? So we know that magnesium is going to be +2. All right? Similarly, we also know that for group 6A, the oxygen almost always is going to be oxidized to -2, and the sulfide is going to oxidize, the sulfur is going to oxidize to -2, becoming sulfide, and oxygen is becoming oxide at -2. So we know that the oxygen here is going to be -2. Remember, though, that there are 4 of them. So the net charge contributed by the oxygen in total is going to be 4 times this value. We set up a simple equation that has to be equal to 0, and now we're going to generate the equation. So for the magnesium, it's going to be 2 plus the chromium, which is the unknown here, right? Because this guy is a transition metal, and it can have a whole variety of different oxidation states. To restate that in English, chromium, being a transition metal, can have all kinds of different charges when it appears in a compound. So this is our unknown. And then we're going to be adding that to the oxygen content. There are 4 of them. Oxygens are -2, like this. So we're going to have 2 plus the unknown -8 is equal to 0. So chromium -6 is equal to 0. So the chromium in this compound is equal to +6. And I'll just write it in here like that. All right. Now, let's look at another example. In this case, let's look at a polyanion that does not have a cation with it. And how do we deal with this animal? All right. So the key thing here is we're still setting up an equation, all right? And what you need to pay attention to is the fact that you've got this charge. So this whole molecule, when we add together the oxidation numbers, or the charges of the elements that are in here, they have to sum to equal this charge. So our equation is going to be equal to -2. That's the key with an anion, or a cation for that matter. Any kind of molecule that has a charge, you're going to set your equation equal to whatever that charge is. Now we've got two chromiums here, and again the chromium is the unknown because it is a transition metal and it can have many different oxidation states, or to say it in English again, it can have several different charges depending on the context in which you find it. And then we're going to be adding this to the oxygen content. There are 7 oxygens here, and again the O is going to be O-2. So we put in the -2 here. So the equation will be 2 chromiums -14 is equal to -2. That's the equation. So we're going to have 2 chromium is going to be equal to 12. So the charge on the chromium is equal to +6. Now, even though there's 2 different examples here that ended up that focused on chromium and that have the same oxidation number, please do not make the mistake of thinking that your chromium, every time you find it in a compound, is going to be +6, because that's just simply not true. Alright, and we can work a quick example that actually proves that. Let's look at this one where we have chromium oxide, and I won't use the Roman numeral. I won't use the Roman numeral here to indicate this, so that you can see what's going to happen. I don't want to give it away what the chromium is here until after we run our little equation. So again, now this compound does not have a charge on it, so we're going to set our little equation equal to 0. Remember, the oxygen again is -2, so our equation is going to be Cr, and since there's only one oxygen, it'll be Cr -2. So in this case, the chromium is equal to +2. And that just illustrates the fact, being a transition metal, that the oxidation state, or the charge on that particular element, will be determined essentially by the relationship it has with the other atoms where you find it in a particular compound. So the bottom line is this thing can change depending on who the chromium is bonded to. Alright, and with that, I'm going to go ahead and close the video.